Very good. So let's just start with the previous year gate question for non-isothermal reactor. So in this particular lecture, I'll be talking about some concept that is related to non-isothermal reactor, and as well as all of these previous year gate questions we will see one by one. So let's just start with first question. So here you can see in this particular problem, a reaction is getting converted into B is conducted in an adiabatic plug flow reactor. So pure A at a concentration of 2 kilomole per meter cube. So first, whenever we see the question, first we should read the question carefully, and after that, the data that has been given in the problem, you can write the data on your paper or a scribble pad that will be given to you in your gate examination. And after writing all of these data, you can start solving the problem. So here you can see that pure A at a concentration of 2 kilomole per meter cube is fed to the reactor at a rate of 0.01 meter cube per second. And the volumetric flow rate is also given to you, that is 0.01 meter cube per second at a temperature of 500 Kelvin. So the inlet temperature of the reaction mixture in the reactor is 500 Kelvin. If the exit conversion is 20%, then exit temperature, you are supposed to calculate the exit temperature, right? So let's try to understand. So here you have a plug flow reactor, you can see. Fine. So this one is the plug flow reactor, this one is the inlet, and this one is the exit. So here you can see the inlet concentration which is given to you, Ca naught is equals to 2 kilomole per meter cube. So the unit is very, very important here. So you should take these things in your mind. And again, volumetric flow rate, that is equals to 0.01 meter cube per second. Inlet temperature T naught I am assuming is 500 Kelvin. And if conversion XA is given to you, that is 0.20, you are supposed to calculate T, that is the exit temperature, right? Okay, so when we talk about the and if this reaction is getting converted into B is taking place in this plug flow reactor, for this particular reaction, delta H of reaction is also given to you, enthalpy of reaction minus 50,000 kilojoule per mole. And again, the heat capacity of Cp of A, which is equals to Cp of B, which is equals to 100 kilojoule per kilomole Kelvin. Cp is given. So you are supposed to calculate exit temperature. So when we do the energy balance in plug flow reactor, we get the exit concentration T, that is equals to T naught plus obviously minus delta H naught of R, and obviously Fa naught 0 to Xa and dxa upon summation of Fi Cpi. Okay, so what is meaning of Fi Cpi? So summation of Fi Cpi can be written as obviously Fa naught into 1 minus Xa Cp of A plus Fb naught plus Fa naught Xa Cp of B. Why? Because whenever a reaction is getting converted into reactant into product, so 1 moles of A is getting converted into 1 mole of B. So Fa naught Xa moles of A will be getting converted into Fa naught Xa moles of B. So here you can see Cp of A and Cp of B is equal. So if I take common Cp, so you can say Fa naught minus Fa naught Xa plus Fb naught plus Fa naught Xa. So here Fb naught is 0 and Fa naught Xa will get cancelled out. So finally you will be left with Fa naught and Cp, right? So Cp of A and Cp of B is equal. So you can write any of this. So now these things I'll substitute here and I'll get this thing. So T will be equals to T naught plus minus delta H of R. So that will be equals to 50,000 kilojoule per mole. So multiply with 10 to the power 3. Multiply with 0 to Xa and dxa divided by this is your Fa naught and Cp of A. Anything you can substitute, either Cp of A or Cp of B. So what is C naught? T naught is given to you is 500 Kelvin. So now you can substitute T is equals to 500 plus your 50,000 multiplied with 10 to the power 3 multiplied with dxa. So all of these are constant. So again there is a Fa naught here. So Fa naught is constant, it will get cancelled out. And again Cp is constant, so 1 upon Cp of A will be taking common. And you can say dxa integration is your Xa only, that's it. Okay. So your exit conversion is given to you, that is 20%, and the CP is given 100 kilojoule per kilomole. Is that clear? So the temperature can be written as your 500 plus 50,000 multiplied with 10 to the power 3, 1 by 100 kilojoule per kilomole. And the enthalpy of reaction is kilojoule per kilomole, and this is also in kilojoule per kilomole that is given to you. Kilojoule per kilomole, kilojoule. Okay. And what is the Xa? Xa is 0.2. 0.2. So if I'll remove these things, sorry, this is 1010. So you will cut these things. So you will left with T is equals to 500 plus 50 multiplied with 10 to the power 3 into something I am mixing here. 500 Kelvin, 20% conversion to kilomole per meter cube. Concentration FA note and volumetric flow rate is given. Okay, kilomole. Okay, and this is also in kilojoule per mole. Kilojoule per mole. It's fine. Multiplied with 2. So T can be written as 500 plus 50. So sorry, here kilojoule is there. So this 10 to the power 3 will not be there. Why? Because I'm writing in kilojoule, something like that. So directly I'll be writing. Right. So this 10 to the power 3 will not be here now. So that is only 2. So 50 into 2. So temperature will be equals to 500 plus 100. That is equals to 600 Kelvin. So here you got the exit temperature of the reactor is 600 Kelvin, and which is your option C is correct. Is that clear? So this was the first question, that is based on the energy balance or calculation of exit temperature of plug flow reactor. Okay. Now I'll be moving towards the next problem of today's lecture, and let's say, I don't know. Okay. So this problem is also very important kind of problem, and there is a good concept regarding this problem. So here you can see a batch adiabatic reactor at an initial temperature, right? So here there is a batch reactor, and the initial temperature T naught I am assuming is your 373 Kelvin is being used, and a reaction A is getting converted into B is happening here, and heat of reaction. So delta H of reaction is given to you minus 1 kilojoule per mole. So in this particular problem, I'll suggest you every time whenever you are you see the question, no, try to put the question or try to see the unit. It's very important, because most of the time you'll see all of these parameters is having different units. So there is high probability of making some kind of silly mistakes. And delta H of reaction is given, and the heat capacity of both A and B is equal. So Cp of A, that is equals to Cp of B, which is equals to how much? 50 joule per mole Kelvin. The temperature rise after the conversion of 0.5. So Xa is given 0.5. So here this batch reactor is there. So let's try to understand the heat balance reaction of batch reactor and plug flow reactor is exactly similar. So I can write T, that is equals to T naught plus minus delta H of R and FA naught. But here this flow reactor is not there. So in place of FA naught, you can write N naught and 0 to Xa dxa upon summation of Fi Cpi. So since reaction is happening, like A is getting converted into B. So in place of Fi here, you can write Ni Cpi similarly. So you are supposed to calculate the rise of temperature. So what is rise in temperature? So temperature rise will be T minus T naught. Okay, this is rise in temperature. That will be equals to minus of delta HR and obviously Na naught and integral 0 to Xa. We can write dxa upon NiCpi is you can write Na naught into 1 minus Xa Cp of A plus Nb naught plus Na naught Xa, because the stoichiometry of reaction is given. and obviously Cp of B, something like that. So now delta T, that is the temperature rise, can be written as minus of delta HR and Na naught and integral 0 to xa dxa upon. So Cp of A and Cp of B is equal. Both of these Cp's are equal. So something you'll see here, you can cut, and NB naught is 0. So you can say you will left with Na naught Cp of A, something like that. Okay? Now, so Na naught is constant, so it will get cancelled out. So delta T, that can be written as minus of delta HR multiplied with Xa divided by Cp of A. So delta T can be written as, what is delta H of R? Minus 1 kilojoule per mole. So minus 1 and minus 1 plus into 10 to the power 3 joule per mole. Is that clear? Joule per mole. And Xa. Xa is 0.5, I think, right? And Cp. Sorry. Cp is given 50 joule per mole. So this is 50 joule per mole. So if you put these things, 500. So delta T will be equals to what? 1000 divided by 100. So that is equals to 10. So change in rise in temperature is equals to 10 degrees centigrade. Is that clear? So since what we have seen till now, that the energy balance equation for both plug flow reactor and the batch reactor are same, that's why I have written this formula for the energy balance here, and to calculate the exit temperature of the batch reactor. I hope these things is clear to all of you now. I'll be moving towards the next problem of today's discussion, and this problem is based on the CSTR reactor, right? So I don't think some data has been taken. I'll remove this data and I'll again. Okay. So let's see. Here the question is based on the energy balance in continuous STR tank reactor. You can see a CSTR is to be designed in which an exothermic liquid phase first order reaction is carrying out. So here you can see the exothermic first order liquid phase reaction is happening in this CSTR. Okay, and the reaction is getting converted into a reactant A is getting converted into product R. The reactor is to be provided with a jacket in which the coolant is flowing. So this reactor is provided with a jacket in which coolant is flowing, right? In order to maintain the adiabatic condition, right? So that's why these things is given to you. And the inlet concentration of reactant A, that is given 5 kilomole per meter cube, and conversion of the reactant in this reactor is 0.5. Feed temperature is equals to the reactor temperature that is given. So T naught is equals to 40 degrees centigrade, which is equals to T, that is equals to 40 degrees centigrade. So feed temperature and reactor temperature is equal. So you can see here. First, now rate constant, the value of K that is given to you, that is 1 minute inverse. 1 minute inverse, and enthalpy of reaction, delta H of reaction, that is equals to minus 40 kilojoule per mole. Is that clear? Minus 40 kilojoule per mole. And again, density of reaction mixture is given 1000 kg per meter cube, and Cp is given 4 joule per gram meter degree centigrade, and obviously volumetric flow rate is 10 to the power minus 3 meter cube per minute. Okay, so you are supposed to calculate the amount of heat to be removed is. So since this exothermic reaction is happening in the reactor and the feed temperature is equals to the inlet temperature, right? So sorry, reactor temperature is equals to inlet temperature. So the amount of heat that is being removed, right? Because you want to maintain the adiabatic condition. So definitely from this particular cooling jacket, you are supposed to remove some heat so that the adiabatic conditions can be, sorry, exothermic reaction is happening here. So you are supposed to calculate, remove the heat while using this jacket. So how much heat you are going to remove from here, that Q can be written as minus delta H of R, Fa naught and Xa. Is that clear? Why these things is happening? because exit temperature is also not given to you. So the thing is that if reactor temperature is here, let's try to understand one thing. If reactor temperature is here, the exit temperature will be also T equals to 40 degrees centigrade, right? Because in continuously stirred reactor, the process variable which is inside the reactor will be equals to the at the exit. So if you do the energy balance, so what you can say, so Fi naught, or since reactant is your A, so you can say Fa naught Cp of A and T minus T reference, right? And if I'm assuming T reference is equals to 40 degrees centigrade, which is your reactor temperature, and T reference is equal. Why? Because this is also 40 and this T reference is also 40 plus uh, minus delta H of R Fa naught Xa minus Q, that is heat removed, plus and minus, sorry, the amount of heat which is removed, that is minus Fa Cp of A plus Fr Cp of R, and obviously you can say T which is equals to 40 degrees centigrade minus T at the exit is 40 degrees centigrade, right? That is equals to 0. So since this will be 0, this will be 0. So what is the total amount of heat that is removed, that is equals to minus delta H of R enthalpy of reaction into Fa naught Xa, that's it. Right, so this is some tricks that you need to apply here, because you have to understand, because here the confusing part was that some students will do some mistake there, that some students will take this part also. So confusing, you have to keep this things in your mind whenever we are dealing with the continuously stir tank reactor. So your exit temperature will be equals to the reactor inlet temperature. So now let's calculate the parameters now. So Q, that will be equals to, what is delta H of our reaction? Minus 40 kilojoules. So 40 and 40, 40 into 10 to the power 3 kilojoule into Fa naught. Fa naught is not given to you, but here you can see Ca naught and volumetric flow rate is given. So 5 kilomole per meter cube and 10 to the power 3 millimeter. So 5 kilomole per meter cube. So that is 10 to the power 3 multiplied with 10 to the power minus 3 divided by 60. And what is Xa? Conversion in the reactor is 0.5. So that is your half. So you can cancel out these things, and Q can be written as 40 multiplied with 5 divided by 60 multiplied with 2. So that is 2 into 20, 20 into 3. So into 10 to the power 3. So 5 by 3 into 10 to the power 3. So 5 by 3 kilowatt. So this one is the answer. Q is equals to 5 by 3 kilowatt. Okay. So here you can see the answer is option C. All of these questions have been asked in the gate. This question has been asked in the gate in 2023, and really this is very, very important question. Lots of concepts were there that we learned. Now I'll be moving towards the next question, and this question is a theoretical question from exothermic reaction. You can see then exothermic reaction takes place in adiabatic reactor. The product temperature. Uh, so since you can see that any reaction, let's say if you have a reactor, any reaction is happening in adiabatic reactor, right? So in adiabatic condition, you are not supposed to remove the heat. So whatever the heat which is being generated inside the reactor, that will be there. So if heat exothermic reaction is there, so if this is T naught and if this one is T, so let's say if reactant is entering at a temperature T naught, okay, but exothermic reaction is happening. So due to this reaction, some heat will be getting evolved, and due to this particular heat, what will happen? The temperature of this reactor here, the temperature inside the reactor will increase, and this temperature is also equals to, let's say, this temperature. So means the product temperature will be also increasing, right, due to exothermic reactions condition. So you can see that it is always greater than the feed temperature. Why? Because due to exothermic reaction, the outgoing fluid from the reactor will be at higher temperature compared to the incoming fluid, which is feed. Right? This is the concept here. And when we talk about the endothermic reaction, definitely for the endothermic reactions, the outlet temperature of product will be less than the inlet temperature. So if I tell you the concept regarding these things, so let's say if I'm talking about T is equals to T naught plus minus delta H of R, and obviously Fa naught Xa upon summation of Fi Cpi, right? So you can see if I want to plot temperature versus conversion, right? So with increase in conversion, what will happen? More heat will be getting generated. And for exothermic reaction, what will happen? Delta HR is negative. So negative negative will becomes positive. So what will happen? If I plot this curve, something like that, temperature versus XA, what you will see, it will start when conversion is zero, it is at temperature T0. And since this is exothermic reaction, this will go like that. The slope will be like that, something, right? And what is the slope of this curve? Slope will be equals to minus of delta HR into FNO divided by summation of Fi Cpi. But if it is endothermic reaction, this will go like that. Is that clear? So this will go like that. So this curve is for your exothermic reaction condition, and this curve is for the endothermic reaction. Is that clear? So this is exothermic and endothermic reaction condition. Okay, this was very conceptual question. You should understand. And again, directly we are not dealing with this concept. There is some mathematics and all of these things are there that I have told you how to, explain logically this kind of problem. Now, after that, I'll be moving towards the next problem of today's discussion. That is, for an ideal, again, this question is a conceptual question. You can see, for an ideal gas mixture undergoing a reversible gaseous phase chemical reaction, the equilibrium constant is independent of pressure, is increases with the pressure, decreases with the pressure, increases, decreases with pressure, depending upon the stoichiometric coefficient of the reaction. So, I think option D will be correct. Why? Because the equilibrium constant is function of pressure and it is going to depend upon the stoichiometry. Let's say AA plus BB is getting converted into CC plus DD, right? A stoichiometric coefficient, sum of a stoichiometric coefficient of product is more compared to sum of a stoichiometric coefficient of reactant. If you will increase the pressure, equilibrium conversion will decrease. And if let's say summation of nu I of product minus summation of nu I of reactant is greater than zero, so what will happen? If you are going to increase the pressure, so K equilibrium will decrease. And again, reverse case, summation of nu I of product minus summation of nu I of reactant is less than zero. So if you are going to increase the pressure, what will happen? K equilibrium will increase. So these are the, you can go you can understand these things from this particular thing. So again, if I talk about the conceptual concept behind this particular questions, I've already made the video. You can go through my YouTube channel and you can go in chemical equilibrium things that I've taught in the chemical reaction engineering concept, and there you can go through all of these concepts. Okay. Now next question, I'll be moving towards the uh, question of 4.7, and this question has been asked in GATE 2024. The question says that an endothermic aqueous phase first order irreversible reaction. So there is a reaction, let's say A is getting converted into B and N is equals to 1. Irreversible reaction is carried out in adiabatic plug flow reactor. So the reactor is a plug flow reactor, right? This reaction is carried out in adiabatic plug flow reactor. So means there is no heat removal, right? The rate of reaction is, so the rate of reaction is maximum at the inlet of the reactor. So see, one more thing is that goes through maxima along the length of the reactor goes through. So since this is irreversible reaction, if reversible reaction would be there, then the case would be different. But since this is irreversible reaction, so here we have to say there is a different case. So whenever there is irreversible reaction, if and this is an endothermic reaction, right? So endothermic reactions, the rate will increase when you are going to increase the temperature, right? So aqueous phase first, and again, this is adiabatic process. Okay. So since you are not going to supply any kind of heat, but since this is endothermic reaction, so what will happen? This reaction requires some amount of heat for moving forward towards the reaction. So if A has to get converted into B, this reaction requires some amount of heat. But due to adiabatic condition, you are not supposed to supply the heat. So what will happen? The rate of reaction will be maximum at the inlet. Rate of reaction, let's say if I am planning minus RA versus L, if I am plotting this curve, so this one is your length of the reactor. So rate of reaction will be maximum at the inlet, and after that it will start decreasing, something like that. Okay, so you can see goes through maximum along the length of reaction. That is wrong. If it would be the reversible reaction case, then the option B may be correct, but this is wrong. Goes through the minima along the length of the reactor, is maximum at the exit of the reactor, wrong, is maximum at the inlet of the reactor. Okay, so rate of reaction will be maximum at the inlet of the reactor, and along the reactor length it will start decreasing. Why? Because due to endothermic nature of the reaction condition. Okay. Okay, that's it. Now, next question is consider this is again, this question is similar to the previous question that I have discussed right now. So here you can see the consider a reversible exothermic reaction in a plug flow reactor. The maximum and minimum permissible temperature are T max. So again, this reaction is happening in a plug flow reactor. Here you can see, and temperature max is given to you and T min is there. Which of the following temperature profile will require the shortest residence time to achieve the desired conversion? So what is meaning of desired conversion shortest residence time? So this reaction has to reach to a desired conversion. So let's say if a reaction A is getting converted into B, and this is a reversible exothermic reaction. So this is a reversible exothermic reaction is happening. Okay. So if exothermic reaction is there, what will happen? So initially the rate of reaction will be very high. So yeah, so if exothermic reaction is there, then what will happen? In the energy is getting released, right? So the temperature of the reaction system will during the reaction, what will happen? Heat will be generated, right? Once heat is getting generated in the reaction system, so initially what will happen? The temperature will be high. Okay, so once the reaction will progress, right? Once the reaction will progress, and heat will be generated. Heat will be generated, and this is an adiabatic condition. Is that clear? This one is the adiabatic condition. So what will happen? The length of reactor. Again, the temperature will start increasing, right? Reversible reaction passes the maximum. Okay, this one is not adiabatic condition. Consider a reversible reaction. The maximum and minimum permissible temperature is this one. Which of the following temperature profile will require the shortest residence time to achieve the desired conversion? Okay, so you are supposed to calculate the shortest residence time for the desired conversion. So since exothermic reaction is there, so if you are going to increase the temperature, what will happen? The reaction will shift towards the backward direction. So the temperature should be decreased. B. Is that clear? Temperature should be decreased. Now, next question is, and again, this question is from continuous STO tank reactor. That question is been asked in 2004. Great. So here you can see an irreversible aqueous phase reaction A plus B is getting converted into product is carried out in an adiabatic mixed flow reactor. So this mixed flow reactor is adiabatic, and the feed containing 4 kilomole per meter cube of each A and B. So the reaction which is happening here is A plus B, which is getting converted into product P, and the concentration of both A and B is 4 kilomole per meter cube, and the volumetric flow rate is given. So let's say Ca naught will be equals to Cv naught, that is equals to 4 kilomole per meter cube, and the volumetric flow rate is given, that is equals to 8 meter cube per hour. If the inlet temperature, if the temperature of exit stream is 390 Kelvin, so the exit stream is 390 Kelvin, that is given to you. And what is the maximum feed inlet temperature? So you are supposed to calculate what is the maximum feed inlet temperature. Is that clear? Okay, we'll tell you how we can calculate the maximum feed inlet temperature. So enthalpy of reaction, that is delta H of reaction, is given to you minus 50 kilojoule per mole. Density of the reaction mixture is obviously 1000 kg per meter cube. A specific heat is also given, that is 2 kilojoule per kg Kelvin. A specific heat is also given to you. Okay, so the data can be assumed to be independent of the composition. Okay, so whenever we talk about this thing, so since you can see this temperature we don't know, and the exit temperature is there, and if I'm talking about T reference is equals to T exit temperature, right? So now we can balance, we can do the balancing over here. So what we can do here is since you can write rho V naught Ca naught into what? T minus T reference. And I'm assuming T reference is equals to T exit, which is equals to 390 Kelvin. Okay. Plus minus delta H of R, and obviously Fa naught Xa plus again, since this temperature and this temperature is same, so all of these things will be zero, and yeah, so that is equals to 0. Is that clear? So we are supposed to calculate what is the exit, sorry, these things, T inlet. This is our T inlet, and T reference is the T exit. So we can write rho V naught, uh, sorry, this will be your Cp of A or Cp of mixer, rho V naught and Cp of mixer. So inlet temperature T in minus T exit is your 390 plus delta H of reaction is given to you, that is 50 into 10 to the power 3 multiplied with Fa naught. Fa naught is not given to you, but Ca naught is given to you, and volumetric flow rate is given to you. So I can write Ca naught into V naught multiplied with Xa. Xa is equals to 0. So in order to understand, or in order to get maximum inlet temperature, the conversion should be equals to 1. The conversion should be equals to 1. That, and that condition only you can tell, okay, the maximum inlet temperature is there. What is rho? Rho is your 1000, and then see V naught and V naught will get cancelled out, and Cp of mixture is given to you, that is 2 kilojoule per kg Kelvin. So that is 2 kilojoule is 10 to the power 3 into T in, we are supposed to calculate minus 390 plus 50 into 10 to the power 3 multiplied with Ca naught. Ca naught is then 4 kilomole per meter cube. So that is 4 into again 10 to the power 3 x to 0, that is equals to 0. So 10 to the power 3, this will get cancelled out. You can see 2 multiplied with T in minus 390, that is minus 50 into 4. So 2 into 2. So T in minus 390, that is equals to minus 100. What is maximum inlet temperature? That is equals to 290 Kelvin. 290 Kelvin will be maximum field inlet temperature. Is that clear? Okay. So with that, I'll end this lecture, and again in the next lecture, I'll be solving some another problem from non-isothermal reactor only. So this is the series of only PYQ solution for non-isothermal reactor. Okay. Thank you.